There's also another buildup and decay chain that exists for reactors, which is the thorium chain. Thorium can be dug up out of the ground. It exists naturally. There's only one naturally occurring isotope of thorium, thorium-232. Thorium-232, when it absorbs a neutron, will then produce thorium-233. Thorium-233 then goes through a beta decay to protactinium-233, which then beta decays again to uranium-233. And uranium-233 is a good nuclear fuel, like U-235. So when that exists in a reactor, it'll predominantly fission in the reactor and produce power. This particular buildup and decay chain really only occurs in India. It'll occur in any reactor that you put thorium into, but the only country that really uses this cycle is India, where they have a large amount of thorium in their soil and a small fraction of uranium compared to some other countries. Most other countries really haven't explored this particular fuel cycle in much detail. The other thing then that gets produced, as those fission reactions occur, we then produce fission products. And those fission products will also go through buildup and decay chains. Principally when uranium-235, plutonium-239, or U-233 fissions, they're going to produce fission products that are very radioactive with very short half-lives. For instance, tellurium-135, which has a very short half-life. That isotope then will decay to I-135, which then decays to xenon-135, that decays to cesium-135, that decays to barium-135. So as you can see, it's decaying through a mass chain. In all cases, the isotopes all have the mass 135. In some cases, those isotopes might absorb a neutron. For instance, in this case, xenon-135 can absorb a neutron and make xenon-136. And xenon-136 is then stable. Xenon-136 also could be produced directly from fission. And so as you irradiate a fuel, you'll produce these radioactive isotopes. And these radioactive fission product isotopes actually dominate the radioactivity of the fuel when it's first discharged from a reactor. The distribution of these isotopes you get is somewhat odd. That as a function of mass chain, you get this, what they call the characteristic double hump curve, which is where a very non-uniform distribution, where principally most of the fission products that are produced have masses around 90 AMU or 150 AMU. And you have this sort of deficit, this valley in the middle, as well as there's very few isotopes that are produced at the very high masses and very few at the very low masses. This particular curve then shows that the actual distribution of fission product isotopes that you'll expect to see in a reactor depends on what the particular reactor design is and how it's operated. And so you'll get these sort of different but predictable distribution of these isotopes. These next couple of pictures just show some of the different chemical forms of materials that we'll expect to see throughout the fuel cycle. So the first one here shows you U308. So you might, for instance, expect to see uranium ore, which is something that we would dig up from the ground. There's no picture of uranium ore shown here because it's pretty much just dirt, so not very interesting. But that uranium ore then will be milled to a concentrated product, which we call U308 or yellow cake. It's called yellow cake for a fairly obvious reason. It's a yellowish-orange color. And yellow cake itself is a solid, powdery form that is fairly non-dangerous. As you can see, this individual isn't wearing any special protective clothing. He's just wearing a couple of plastic gloves, mostly just to keep the material from getting contaminated from him, not so much him from the material. Another form of uranium that we would expect to see is UF6, or uranium hexafluoride. Uranium hexafluoride is the only chemical compound of uranium that exists in gaseous form at fairly low temperatures. At room temperature, it actually exists as a solid crystal, and then at slightly above room temperature, it turns into a gaseous form, and that gaseous form of uranium is then what is used in gaseous diffusion plants and gas centrifuge plants that you might have heard of. That uranium hexafluoride then, after enrichment, could get produced, turned into uranium dioxide, which is the principal form of uranium that we see as nuclear fuel in reactors. And uranium dioxide is a dark-colored ceramic. These particular pellets are, these aren't to scale, these are blown up, but you'd expect them to have a diameter that is similar to the diameter of my pinky. Those uranium dioxide pellets then would get loaded into steel tubes or metal tubes. Those tubes are typically about 14 feet long, so they're very long, but again very skinny, about the diameter of my pinky. And the typical tubes that are used in the United States are made of what they call zircaloy, which is a zirconium alloy. Those tubes then get welded together and loaded together into a fuel assembly. So this fuel assembly, which is a typical PWR fuel assembly, or pressurized water reactor fuel assembly, is about 14 feet long and about 8 inches on a side. That assembly weighs about a metric ton. That particular assembly then would get loaded into a reactor and irradiated. And after that comes out of a reactor, then you would have the irradiated fuel assembly. And you may or may not be able to see in this picture, but that assembly is in fact glowing blue. That blue glow is what we call shrink-off radiation. It's a visible light that gets produced from the irradiated materials when it's in water. And those irradiated materials always have this nice characteristic blue glow, which does, of course, help you know that the thing, in fact, is irradiated. This is a picture of a spent fuel assembly at the Comanche Peak reactor, which is a 2-unit nuclear power plant outside of Dallas, Texas. All right, so that goes through some of the basic materials that we would expect to see in the nuclear fuel cycle.